So today's video is going to be the introduction to Chapter 10. In Chapter 10, we are going to look at a new type of function, and we're going to introduce that function right here. So the first type of function we're going to study now in Chapter 10 is a radical function. And we can see it's a function that contains a radical expression. In other words, it has a radical sign and then something under that radical sign. And the way I just want to frame your mind over here, let's just recall we've seen types of relationships before. Like we know what a linear relationship is. If we think about a linear relationship, they make lines, right? Maybe it looks like that, or maybe another thing looks like this. But those are linear relationships. We just got done studying our quadratic relationships. Quadratic relationships, again, just have a different shape of a graph. They could make U's that look up like this. Sometimes they can be down like a frown. We can move them all over the place. So for today, we're introducing a new type of function, which is radical. What we'll see here is the radical functions, again, can look like a lot of different things. They can look like that, or maybe we can flip them over and move them around. It looks something like that. But that's our goal for today, is to look at those types of functions. So we are going to start, just like we did with radicals, by looking at the parent function of all square root functions, and that is just the square root of x. Now, the first thing when we make tables using square root functions, we're going to have some sort of input for x, and then our output will be determined by taking the square root of that. When I ask you to make things with the table, it's usually pretty hard to find square roots of numbers that are not perfect squares. So when you're making a graph using a table, I usually have you just choose x values that'll make the radicand. Remember, the radicand is just a word we've defined up here as whatever the thing under the radical sign is. Have that be a perfect square. So since this number here, x is our radicand, we want x to be perfect squares. So 0, 1, 4, 9, 16, so on and so forth. So if I plugged in 0, the square root of 0 is 0. We'll plot that point. The next perfect square is 1. The square root of 1 is equal to 1. So I'll plot that point. The next perfect square we know is 4. The square root of 4 is 2. So we'll plot that point. 1, 2, 3, 4. 2. And the last one that's going to fit on this graph right now will be 9. The square root of 9 is 3, and that'd be the point right here. So when we connect those, it's going to make a graph that looks like this. So this is our general shape of a quadratic. The general shape of a quadratic kind of looks like a little check mark. It starts somewhere, and it increases like that. So that's one thing we want to see from this graph. Just like we did with the quadratic parent function, we need to know a bunch of stuff about the parent function of the radical, so we can use that to study other equations that look similar, like their transformations, but are a little bit different. So the first thing we need to know is our domain. So the domain for this one, there's two ways we can think about it. What are all the x values on the graph? Or the second way we can think about it is what x values could be used as inputs. And I think that's the easiest one to help us with our domain right now. So what we know about the square root is whatever's under the square root. So if I have a square root sign, whatever is here, whatever this thing is, that number here, I can only take the square roots of numbers that are 0 or bigger. Right? No negatives. We can't take the square root of any negative number. So if I asked about what x values could I plug into this equation, those x values that I choose, they have to be 0 or bigger. So the domain of our radical function is all the x values that are bigger than 0. On our graph, we can see here that the first point has 0, 0. And as I follow that graph, my x values like 1 and 1 and 4 and 9, my x values are just getting bigger and bigger and bigger. So if I wanted an x value of like 107, I could go find that somewhere on my graph, but I'll never be able to graph a point with a negative x value. Now the range are all the y values on the graph. Similar to how we saw that with quadratics, there's usually a highest and a lowest point. I can visually see here that all the points on my graph are above that line y equals 0. So graphically, we can see that all the y values on our graph, all the y's, are bigger than or equal to 0. The way that we can remember that is from our domain. If I can only take the square roots of numbers that are 0 or bigger, that means if I were to take the square root of 0, I get 0. If I start taking the square roots of numbers that are bigger, like 9 or 16 or even 64, the outputs that I get are also 0 or bigger. So those two facts you need to have memorized about your parent function, right? You need to know the domain of the radical function is all the numbers that are 0 or bigger for the x values, and the range, the outputs, are all 0 or bigger. And when we're talking about the graph here, we want to know the starting point of that graph. And the starting point is what I labeled as 0, 0. We're just going to call that the starting point for our language. So the starting point is at 0, 0. Now we're increasing always. So in other words, it's going to be increasing whenever the x value that I choose is bigger than 0. And this graph is never decreasing. And again, we can see that if we were to pick a point on the curve and follow that, we're always just going up and up and up. So these facts you need to have memorized about the parent function. Again, the domain, the range, what is that starting point, when is it increasing, and when is it decreasing. So let's do a quick example of how we would make a table and then use that to make a graph. So when we're doing something that's a little more complex, so here there's a few things we're going to look at. We see a square root sign. So that tells us the graph should somewhat resemble that general square root shape of the parent. So that's the first thing we're noticing, but we're also noticing that this is now different than the parent. So it's going to be moved around or might have a different domain and range, but it's different than the parent. But we're just going to, again, practice making a table. So again, we're reminding ourselves that whenever we're trying to make a table, it's really hard to estimate square roots that we don't know, especially if we don't have a calculator. So when we're making the table, we want to choose x values that'll make our radicand a perfect square. So what we're doing is we're choosing x's. So I'm going to write down here. So we're going to choose an x. So our radicand, right, the number under the square root, which for us is x minus 1, right? This is the only thing under the square root. So we want that value of x minus 1 to equal a perfect square. Now, a perfect square, there's a lot of them, right? The squares that we know would be 0. We know the square root of 1. We know the square root of 4. We know the square root of 9, the square root of 16, so on and so forth. So that's how I'm going to choose an x value. So if I want the thing under the square root to be the first perfect square I know, like 0, that means I would choose the x value of 1. So in my table, I'm going to choose x is equal to 1. So if I wanted to find the y value for that point, I would just plug in 1 for x. So 1 minus 1, and then not under the square root of plus 1. So the square root of 0 plus 1, that's just the number 1. So at the point 1, 1, we have a point. Now, I also want to use the next perfect square, x minus 1, whatever that number is. If I could get it to equal the number 1, I'd be taking the square root of 1, in which case the x value I used would be 2. So I'm going to choose 2 in my table. So to find the y value, I'd plug in 2 for x, so 2 minus 1, and then outside of that plus 1. So simplifying under the radical, I get the square root of 1, right? That number is a perfect square that I know. So this is equal to 1 plus 1, which is just the number 2. So at the point 2, 2, that is also on our graph. So the next perfect square that I want to use, I know the square root of 4. So I'd want that number, x minus 1, to come out to be 4, in which case I'd want to use the x value of 5. If I plugged in 5 into my x value to find the y value, I'd take that 5, subtract 1, find that square root, and then add 1, which means I'm really taking the square root of 4 and then adding 1, which is just 2 plus 1, which comes out to be 3. So at the point x value of 5, 2, 3, 4, 5, we have the point 3. And do one more. I also want that x minus 1 to equal 9, right? Because I know the square root of 9. So if I plugged in 10 for x, I get the square root of 10 minus 1 and then add 1. Well, that's just the square root of 9 plus 1, which is 3 plus 1, which we get as a 4. So the x value of 10 has an output of 4. And then I connect them with that general shape there. So I can see here that this has a little different starting point, but this is our starting point. Right, in this case, the starting point looks like it was moved over 1 and up 1, but our starting point was 1, 1. And we can see there's some differences. Like this is always increasing, but it's increasing whenever I choose an x value that's bigger than 1, just because I'm starting at the x value of 1. But the domain and the range we'll talk about on a different day. We're just kind of looking at the graphs for these right now. Now, more generally, we can make a table and then use that table to make a graph. But if we don't have a table, we can also look at transformations. And when we look at transformations, or that's what we're moving on to down here in purple, aside from making a table, we can graph square root equations using transformations. And that's what we're going to address here. So here, I just gave us a reminder. This was back from chapter 10. When we had a parabola in vertex form, We talked about these things, how like this a value here could flip it, it could stretch it, it could shrink it. This h value could move right or left, and this k value move the graph up or down. So in similar light, we're going to notice that all square roots can be written in that same form. So the first thing we want to say is any square root function can be written like this. Just like with a parabola, we know any parabola could be written in vertex form. So if any parabola can be written in vertex form, we just use the form to track the transformations. So we are going to do the same exact thing with our square root functions. What we're going to do, we're just going to visually show this really quickly so we can see that it does work out super nice, like in regards to what we already know. So let's go to Desmos real quick and let's type f of x is equal to the equation that we have there. So we're going to do a times the square root of x minus, and then here I'll use h. Outside of that square root, we have a plus and then a k. And on my version, I am going to add those sliders for my square root. So the parent function, just so we're clear, the parent function is supposed to just be f of x is equal to the square root of x. So in other words, for the parent, we would know that the a value was equal to 1, the h value was 0, and the k value was also 0. So that's where I'm going to start my sliders. I'm going to put the a value, I'm just going to type it in, set that equal to 1. The h value we're going to set equal to 0, and the k value we're going to set equal to 0. So here we should see our classic shape of the radical function. It has a starting point of 0, 0. So the first thing we're going to talk about is what does that a value do. So I'm going to hit play on the a slider. We're going to see a few things. So it looks like it's getting stretched out. Now it's stretching down, and at some point it's flipping over. So what we should see here is that the a value actually does the same thing as it did with the parabola. So the first thing, it can flip. So if a is negative, the graph is vertically flipped. What we see here, if it starts like this, vertically, the general shape of the graph normally is like this, right? The general shape looks like that. But if I flip it over just by making this a negative number, then it flips over like that. So it only flips over, it's a negative. And then the same thing that we're going to see here, it's a little bit harder to see on the picture, but the negative is the only thing that flips it over or not. If I make this number bigger, like 5, it's more stretched out. If I make that number smaller, it's less stretched out. So regardless of the sign, if the absolute value of a, if that number is bigger than 1, we see our vertical stretch, which is a little bit hard to draw, but we'll just write it in words. If the a value, regardless of the sign, so that's why I put it inside the absolute value, if it's less than 1, that's going to be a vertical shrink. And that is the same exact thing that we saw with our parabola. So let's set a back to 1, which is what the parent function is, and we're going to hit play on the h value, and we can see the h value is moving that starting point left or right. So we'll label our h value, and it's actually going to follow the same rules as it did with the parabola. So it's going to move right if it's x minus a number, and then it's going to move left if it's x plus a number. So again, the thing under the square root will determine if it moves right or left. And then lastly, we should already have a guess for that k value. So I'm going to put h back at 0, or close enough. And the k value, we can see is just making that graph move up or down. Very similar to the parabola. So I'm just going to label that on our notes here. At this k value, it'll move up if it's a plus k, or plus a number, and it'll move down if it's minus a number. So we do want you to see that we can graph radicals very similar to how we graph quadratics using transformation. The only thing that's really different is the shape of the graph, but the letters all tell us to do the same exact thing as they did over here. And again, that's just a reminder from our notes that we've done in chapter 8 with our quadratics. So feel free to go back and review that. So we're just going to do a couple examples with that transformation to sum up our notes. So how could we quickly sketch a graph of this by using the transformations? So here we see a number under the square root, and the number under the square root that we wrote in our notes from before should move that graph left or right. So I'm going to see right here, it's going to move left if it's plus a number. So this graph is going to have moved left 4 units. And that's it. So instead of the start being at 0, 0, it moved left 4 units. So that new starting point is right here. And then it always has that general shape of the radical. And that's all I'd be asking on this one. So we'd label the starting point at -4, 0, and then we know the general shape. So one that's a little more involved, let's look at the next one here. So the letter out front, the a value, since a is positive, so the absolute value of 3 is greater than 1, that tells us that there's going to be a vertical stretch. Going back to under the square root, we see plus a number. So as we wrote down from before, plus a number means we're actually going to move left that many units. So moved left 1 unit. And then the number at the end moves the graph up or down. So since it's a negative, right, we wrote ourselves, if it's minus a number, we move down. So we move down 5 units. So what we're thinking at here is the parent normally started at 0, 0, but we moved it around and stuff like that. So if we moved it left 1 unit and then down 5, so left 1, 1, 2, 3, down 5, that's maybe about right here. We'll estimate that point as left 1 and down 5. So that's the starting point. And once I know where the starting point is, I know the general shape is a radical. So it always follows that general shape. And that's all I'm asking for there. We can also label the y-intercept if we wanted to. For the y-intercept, we know that x is just equal to 0. So if I plug in 0, the reason we tend to stay away from that at times, this one doesn't actually work out bad, is we know that this is -2, but it doesn't always work out that well. So sometimes you can label the y-intercept, sometimes not. The direction should always say. We'll do this last one here as an example just because we can see that there's a negative. So this is going to flip the graph over. And when I think about the absolute value of -2, I don't care about the plus or the minus. That's what flips it over. But the 2 itself is bigger than 1. So that is going to be vertically stretched. And that one's hard to draw. So as long as you write it down, that's all we really care about. The number under the square root is a minus. So if it's under the square root with a minus, it actually moves to the right. So that's going to tell us to move our graph to the right 3 units. And the number at the end is a plus. So plus, as we wrote down before, if it's a plus at the end, it's actually going to move the graph up that many units. So this is going to move up 4 units. So we'll put the starting point first. So instead of starting at 0, 0, we move to the right 3 and up 4. So 1, 2, 3, 1, 2, 3, 4. So let's say that's our starting point right here. And that is the point 3, 4. Now normally it would go up like this, but we flipped it. So instead of going up like that, we should flip it over and it should go down like that. And that is our sketch for that. And that's all we'd have to do. So summarizing our notes for today, we introduced a new type of function called the radical function. And as we said, a radical function just gives us a new shape of a graph. So whenever we want to make a graph, we can always fill out a table. So that's one thing we need to get out of today. We're making a table, we tend to use numbers that evaluate to perfect squares. So we looked at the parent graph. We saw its general shape was kind of that. I don't know what to call it, but that's the general shape. And then we learned the facts. The domain is x is greater than 0 or equal to 0. The range is y is greater than or equal to 0. We know the starting point when it's increasing and when it's decreasing. We did an example of using a table just so we could practice choosing x values that actually made our radicand something we could evaluate without a calculator. So just a skill to practice, and then we graphed it. And then we looked at the transformations right away. Very similar to the parabolas, we know what all the letters do. So if I was given an equation, I can tell you the transformations and use that to sketch a graph. So that is your notes for today.